of beta vector, beta 1, beta 2, beta 3. It's the work form, it's the flux form. So obviously, you know, I mean, algebraically, you might wonder what happens when you take the wedge product of two work forms. Like, what happens with that, right? So what happens if we take, say, omega sub A vector, wedge omega sub B vector? What happens with that? You know, what's this equal to? What's that? Here, let me try a simple one. How about this? Omega wedge, let's say 1, 0, 0, wedge the omega of 0, 1, 0, right? So what's this one? That's exactly dx, right? Wedge with dy, which is this is the flux form of what? What vector? According to our definition. Yeah, so conjecture. I mean, if it worked for one vector, pair of vectors, it must work for all, right? But yes, omega A, wedge omega B is the flux form of the cross product of A and B. In fact, this conjecture is true, but I will leave the proof to your homework. Ah, finally. What do you think happens? Let's try it out on a simple example. What's an example? What example am I on? I don't even know. 2. Example 3. What happens if we say, I don't know, how about this? Omega, if you'll let me fall back to some of my calc 3 notation, omega 3x hat. Oh, that's too awful. Look at this. This looks so awful. Yeah. So that's my stupid unit vector notation from calc 3. But anyway, so this is already, we know this is the flux form of 0, 0, 1, right? Wedge with the work form of 0, 0, 1, just to be more explicit. I mean, this we just worked out in example 2. So let me be more explicit. This is what? This is dx wedge dy, right? Wedge with what? dz, yeah. That doesn't really give me much sense of what's going on, does it? Let's see here. I need a more interesting example. This example is just too dumb. What if I take, let's see here, 3 dx dz wedge dx plus 4 d sorry, that was supposed to be, I'll get my act together here eventually. That was supposed to be dy wedge dz, and then 4 dz wedge dx, and then 5 dx wedge dy. So take that, all right, and let's take the wedge product of that with, I don't know, like 13 dx plus 6 dy. How's that work? So what that gives us is 39 dy wedge dz wedge dx, all right, plus 4 times 13, which is 52 dz wedge dx wedge dx, plus 65 dx wedge dy wedge dx plus 18 dy wedge dz wedge dy plus 24 dz wedge dx wedge dy plus 30 dx wedge dy wedge dy. Now if you've been paying attention, you realize that I've written down some things I didn't need to write down, right? Yeah, anytime we have a duplicate differential, that wedges to 0. So like this is 0. These guys combine to give you 0. When you flip the, you get a minus from flipping dx and dy, but then you got dx wedge dx, which is 0. Again, this is going to be 0 as well, and this is 0, right? So what do we get? We get 39 plus 24, right? Dx wedge dy wedge dz. You notice that I move put the dx in the front. I have to do 2 flippy flops, which gives me a net of plus because everyone's a minus. So two flips is, yeah. What's the significance of this number? How does this relate? So if we look at the vectors 3, 4, 5, and the vector 13, 6, and of course there's 0 dz's, right? How do you get from these two vectors to that? Right, it's the dot product. Conjecture. If we take work form A, wedge work form B, wedge work form C, that is going to be equal to A dot B cross C times dx wedge dy wedge dz. So the wedge product has the cross product built into it. It has the triple product built into it. These are beautiful results. That's not all. There's also calculus. So calculus here, you already know part of it. If I take a 0 form, right, and I calculate df, what's that? You already know what that is. That's partial f partial x dx plus partial f partial y dy plus partial f partial z dz. This we already know from calculus 3. It continues to be true here. This is called the exterior derivative. Notice we've gone from a 0 form f, and this is the 1 form. It's a 1 form, right? So this so-called exterior derivative, d, is exterior because it takes us from 0 forms to 1 forms. Well, what does it do to a 1 form? What should d alpha be equal to? So here, suppose alpha is equal to alpha 1 dx plus alpha 2 dy plus alpha 3 dz. What's d alpha going to be equal to? It's going to be d alpha 1 wedge dx plus d alpha 2 wedge dy plus d alpha 3 wedge dz. And that's going to be the way we get a 2 form from a 1 form. And if you can do this once, you can do it twice, you can do it a third time, right? What's d beta? Where beta is, as I wrote on the other board over there, it's going to be d beta 1 wedge d y wedge dz plus d beta 2 wedge d z wedge dx plus d beta 3 wedge dx, wedge dy. This gets really old to write out, right? I mean, you see what's going to happen with d of g dx, wedge dy, wedge dz. What happens there? I mean, this is a 3 form, right? So what happens if I take the exterior derivative of a 3 form? This would, of course, be naturally defined to be dg, wedge dx, wedge dy, wedge dz. But cool thing now, what does dg have in it? Well, what is this dg? Well, that's the thing you know from calculus 3 already, right? So what happens here? Yeah, it's automatically 0 because there is no non-trivial 4 form over R3. The top form is the volume form. That's the form of maximal number of wedges is the dimension of the space. So, yeah, that's automatically 0. So, you can already tell me what's the differential of a function. How does this, what is in terms of work, this is the work form of what? This is the work form of partial f, partial x, partial f, partial y, partial f, partial z, right? In other words, the exterior derivative of a 0 form gives me a 1 form, which is nothing more than the work form of the gradient vector field. See, this is what we usually call nabla f. It's pretty cool. Now this one, if your alpha is equal to, say, the work form of a vector field f, then d alpha is equal to, well, it's a flux form because it's a 2 form, right? Homework exercise, you guys can show it. This is the flux form of the curl of f. So the exterior derivative of a 1 form is like taking the curl of a vector field. And if you have beta is the flux form of a vector field G, then the exterior derivative beta is, guess what? Well, it's got to be a volume form. What's the scalar that multiplies the volume form? Care to guess? It's the what? Yeah, it's the divergence. Yeah. It's nabla.g. So with this single concept of the exterior derivative, we're able to talk about the curl, the divergence, and the gradient, all in terms of one sweeping concept of differentiation. And there are things that are generally true for the exterior derivative. Like if you take the exterior derivative of a wedge product, it's d alpha wedge beta plus minus 1 to the degree of alpha, alpha wedge d beta. This is true. This is an identity that we'll prove some other day. And there's something else. D squared acting on alpha is equal to 0. So if you take the exterior derivative 2 times, it's all over. That's it. The fact that d squared is equal to 0, for example, if you do it, what happens if you do d df? This is d of omega that, which is d of what? That's the flux form of the curl of the gradient. But of course, we learned vector calculus that that's 0. D squared equals to 0. If I say d of d omega f, right, that's d of the flux form of the curl, which is the divergence of the curl, which is also, as we know from vector calculus, 0. But both of these are just the tip of the iceberg, which is d squared equals to 0. It's been said that all of the equations of physics can be put into d squared equals to 0. I'm not sure how much of an exaggeration. It's not much of an exaggeration. This fact that the twice exterior differentiation of a form is 0 is so insanely useful. But you know, guys, this is more than just, I mean, so we don't have time today to finish this story, but we'll finish. I mean, we're going to be talking about this for days. And I mean, this is a big part of this course is for me to try to explain this as deeply as I can to you guys. So, I mean, classically, I've let a whole half of the course just be about this. McNerney's modifying my behavior a little bit this semester, but I will still tell you many things. Yes, Travis?
Second line from the bottom.
Mm-hmm.
D alpha wedge beta. When you go over to the -1, what's the exponent there?
The degree of alpha. So that's the number of the number of wedges. Well, it's not the number of wedges. It's the number of things being wedged to form alpha. So
that's similar to
the degree of 0 form is 0, the degree of a 1 form is 1, the degree of a 2 form is 2, the degree of a 3 form is 3.
yeah, I couldn't see it.
So
-12.
I'm sorry, I try to write in black. I somehow got off on a red kick here. Now, but so here's why talk about differential forms? Why talk about this? Like, why is it called a flux form? Why is it called a work form? All right. So in future lectures, I'll explain to you that there's a natural concept of integration for forms. We can integrate k forms over k-dimensional objects. And in so doing, we pick up data about the nature of those k-dimensional objects. In the same way that there's a pairing between curves and vector fields, right? Finding the flow to a vector field tells you something about the vector field, and the fact that that curve is a flow to the vector field tells you something about the vector. I mean, there's some sort of duality there. In the same way, there's some kind of very deep connection between submanifolds of dimension k and k forms, which exist on those manifolds. They pick up something about the shape of the manifolds. And this is the basic idea of de Rham cohomology. We can detect shape in spaces by the existence of certain kinds of forms. The thing we do in physics, building potential energy as the derivative of forces from the derivative of a potential energy function, that idea generalizes with forms. The other thing about differential forms, which is really powerful, is that this idea makes sense. It's not a three-dimensional idea. I mean, I showed you 3 dimensions because it's what we know, right? Vector fields. The fact that vector fields can be identified with 1 or 2 forms means there's a fundamental confusion in 3-dimensional vector calculus that we're thinking of 2 separate objects as the same thing. And when you go up in dimension, there's not just vector fields. There's these form fields. They're so-called fluxes. In string theory, for example, you might study electric and magnetic duality, where electric and magnetic fields are not both vector fields. One is a form of a certain kind, the other one's a form of a different kind. I think electric fields are usually identified with vector fields, but the magnetic field gets identified with a flux as you go up in dimension. But the larger point is that this is how you can do calculus that is also paired to some sort of algebraic structure over higher dimensional spaces. But it's also got like low-tech applications, like differential equations. Differential equations, we study exact equations, m dx plus n dy equals to 0, right? It's exact if this is equal to the differential of a function, yeah? So how can I check if the exact equation is exact? If it's exact, then d of df, well, that's 0, right? But that's exactly the condition. What does it mean for dm dx plus n dy to be 0? Well, that's partial m partial y dy wedge dx plus partial n. I should have made this a homework. Maybe I still will. dy equals to 0. And you commute these, and it requires that the mixed partials are opposite in sign. I mean, they have to, well, this gives us partial m partial y minus plus partial n partial x dx wedge dy, right? That being 0 is you need the equality of the mixed partials. That's the exactness condition we teach in differential equations.
I mean, the plus is minus.
No.
Swap dy dx, so it must be turning to a negative.
Well, the reason, the partial m partial x, it's got a dx, but that wedge with dx, 0.
Yeah, I know, like the later on, where you have a partial m over partial y plus partial n partial x. There is a minus there.
Oh, there's a minus. Maybe I didn't write it at the start. It's right there.
I didn't see.
Oh, you didn't see it? Okay. I'm sorry. I need to get better markers. Should throw this thing out. But you know, we can use differential forms to make natural statements about differential equations. In fact, the modern view of differential equations probably says that differential equations should be viewed as differential forms. And solutions should be viewed as manifolds. This is where modern differential equations is. Because that's a coordinate-free characterization of the differential equation, as opposed to these things we do in the class, which are also mired in Cartesian coordinates. Any questions? Yeah.
I have a, this is already told. When you say the form is exact, you mean like there's another form which is like the form m, which like omega is exact when there's another m form, a form m, such that the m.
So yeah, exact. I have not said that yet, but alpha is exact means that alpha is equal to d, let's say psi, for some psi. Closed means that d alpha is equal to 0. So because d squared is 0, exact implies closed. You might wonder, are those interchangeable? Is it true that closed implies exact? And the answer to that question is topological. It depends on the nature of the space. Poincaré's lemma says that if we're working on an open connected subset of Rn, that closed implies exact. And I'll actually calculate that in here. We'll actually work that out. I'll show you how to build psi, that the exterior derivative of psi gives you back the alpha for a K form. There's a wonderful construction, probably due to Cartan. I don't know. It's in all the books, no matter how far back you look. It must be Cartan. The differential form calculus is really from the 20th century, maybe 1920s and onward. It's the work of Cartan and collaborators. But this goes back to Darboux and Pfaff, who was a student of Gauss, right? Was he a teacher of Gauss? I forgot. Student, teacher, student. I don't know. I guess everybody was Gauss's student, whether or not they were his teacher. So let's just say he was Gauss's student. It seems safe. But anyway, I have spent a long, long time trying to understand what differential forms are and how to use them. And I think to me, it's one of my absolute favorite topics in mathematics, and I'm still learning. But I'll try to share with you what I know this semester. This is just my entering my first spiel. I, of course, should give you definitions which are not mired in 3 dimensions. So there'll be summations and stuff, but this is really, I mean, this shows you how to calculate, actually. If you understand what I did, you could easily do calculations in R4 or 5 or whatever. It's the same deal. Basically, the differential just acts naturally and you extend linearly. Yeah, just exactly, yeah. But then there's other things like pullbacks, and there's this. But anyway, McNerney is really, really good. I do intend to follow it. I just will at times speak from my heart. So we have a test Monday, yeah?
Is there a section in the book that?
No, this is not in the book. But my notes also don't have it. No. I forget how much of this I have in my notes. Like a lot of this I like for homework questions, but I will assign homework problems which help make this set in. And we'll talk more about this. We also need to talk, we'll spend some time on the generalized Stokes theorem, which marries this discussion with integration, line integrals, surface integrals, volume integrals. And we'll see that the fundamental theorem of calculus, Green's theorem, and Stokes' theorem are all part of the same theorem called the generalized Stokes theorem. That's possible because this exterior derivative connects these different concepts of differentiation, gradient, curl, divergence, which appear in fundamental theorem, the divergence theorem, and Stokes' theorem. Anyway, so for the test, guys, make sure, I did say you can have a page of notes, right?
Yes.
I just don't want you to copy down the proof that I have said that will likely be on the test, because then it's just silly, right? So, but I want to ask, I'm very likely going to ask you to prove that if we have a function that's Fauché differentiable, if we have another function that's Fauché differentiable, then the sum of those mappings, rather, is Fauché differentiable, and its Fauché derivative is the sum of the derivatives of the respective parts which form its sum. This is a nice, pretty easy thing to prove, but I can in good conscience ask you it on the test if I give you a sheet which also has it on it, because then it's just too silly, even for me. Yeah.
Do we have to prove that the sum of two limits is the limit of two sum? The vector sum, limit of a vector?
You may assume all of the vector limit stuff. Yeah, that I did for you, free of charge. I will not expect you to recreate it on the test, because that was some pretty heavy lifting for me, right? And also, I mean, that thing we did to go from one norm to the other to get the basis that had the orthonorm, you may just assume that your basis has the nice property if it comes up, right? So I want you to use the nicest form of the limit theorems that I've come up with on the test. I don't expect you to, this is not an analysis course, even though I do some analysis, you know. Be sure you can do the tangent space and normal space calculations, right? Those, don't let those get past you, because that'll leave some points. Yeah. What's that? 30 questions on that? I probably have 2. But, you know, they might be worth a lot. Anyway, so I'll see you guys Monday. Oh, Nuka, Travis. You guys